Let's move on to this problem now, which is 2 sum 2. Well, we have already solved 2 sum in our previous videos. So you know what 2 sum problem is. You're given a vector and you're given a target number, and you need to return the indices of if the sum of two numbers is equal to target. It's the same problem here. The only addition is that this time our input array is sorted and it's one indexed. Alright, so if such a problem comes in an interview, we will first start by writing our brute force solution. Brute force solution would be simple. We will just use two loops, and at a single point and at every point we will check the sum. If it is equal to target, we return their indices plus 1. Okay, I'm not gonna code it up. Another solution which we discussed in our 2 sum video was one with a map. So we used map key value pair. For the key we stored the number itself, and for the value we stored indexes, and then we would search for a particular number which is target minus the number which we are at, and we will check if that number exists in our map already. If it does exist, we will have its index as the value, and we can return the current index from our index itself. These two solutions we have already discussed in our 2 sum problem, but let's make use of the fact that our input array this time is sorted. If it is sorted, then we can use its property. A rule of thumb can be, whenever something is sorted, you can think in terms of binary search. Alright, so a binary search solution in this case would be, we already have our high and low pointers, which is the left or right, and we can compare. If our sum is exactly equal to target, then we directly return it. If it is less than target, then we increase our low pointer. This can also be shown in a similar method. It's based on the same idea, but instead of using binary search, you can solve it using binary search also, but the complexity in binary search solution would be n log n, because you're searching, and search in a sorted array is log n, and you are doing that operation n times, so it would be n log n. So that's why it's not useful for us, but we can make use of the 2 sum property, of the 2 pointer property. So we are given that our array is sorted, so let's define our 2 pointers. One will be my left pointer and one will be my right pointer. Right pointer will be pointing to n minus 1. N is nothing but my numbers dot size, so basically the last index. Now we already know that the sum of two numbers should be equal to my target, only then I will return it. So let's write the while condition. Same template, if left is less than right in our 2 pointer solutions, then we check our value. What is value? Value is my numbers of left plus my numbers of right. Okay, this is my value. I am already given target. Now tell me one thing. Okay, tell me one easy thing. Let's look at this first example. What is 2 plus 15? It's 17. So the sum of my left and right pointer values is greater than target. If it is greater than target, then it means that instead of 15, I should have added the number which is to the left of 15. In short, if my sum is greater than target, then I will decrease my right pointer. And if it is less than target, then I want to increase the sum value. And to increase, I will increase my left pointer. So we will make use of the same concept. So if my target is equal to value, then we have found our solution, right? Our solution is nothing but I'll just return here. We will return left plus 1 since it's a 1 based indexing, and right plus 1. Okay. Else if I said my value is greater than target. So we need to minimize this sum. We need to minimize value, and in order to minimize it, I will decrease my right pointer. And else only one case remains, which is our value is less than our target, so we increase our left pointer. And in the end we just return empty, such that because the return type is we need to add a return statement here. So let's run it and see if it passes. It does. So what is the time complexity of it? So we are basically iterating it. Left at most can go to n, and right at most can go from n to 0. But at a certain point they will. So at each iteration, either right is increasing or either right is decreasing or either left is increasing. So our time complexity is nothing but big O of n. And what is our space complexity? Our space complexity is nothing but constant. We are not using anything. We are just using two variables, left and right. So how did we improve from our two-sum problem? In two-sum, we used a map solution, and in that the time complexity was also big O of n, but the space complexity was big O of n because we used a map. In this case, we don't use a map. Okay, let's submit it. Perfect.